All right, welcome to week 2, 1.2, 3, and 4, which is going to wrap up chapter 1 this week. And we're going to piggyback off of what we left off with last week with that 1.1 introduction to a lot of the names and measurements of angles. Okay, we're going to add on to that as well as talk about similar triangles, which we also worked on a little bit last time. Okay, so because we talked about their names already and the various types of angles, we're going to talk about what happens when we have multiple angles. So you can see here I have 2 lines or segments of lines, and now 4 angles rather than 1 vertex and 2 what are called rays. That creates 1 angle only, right? With these 2 segments or lines, we have now created 1, 2, 3, and 4 angles. And with that, you can see I color coordinated these 2 specific types. Angles 1 and 3 are what are called acute angles, but they do have a relationship together with one another, as well as angles 2 and 4. What kind of angles are they, and what is their relationship?
I want to say that 2 and 4 are vertical angles.
Very good. They are what are called vertical angles. And what do we know is true about vertical angles? What does it look like 1 and 3 are to one another?
Vertical as well.
Very good. But what about their measurement, their size?
They're
Equal.
the same. Yeah.
Very good. And somebody said equal, somebody said the same. Are they equal? Are they exactly the same angle? No. This one is facing to the left, this one is facing to the right, and they're using different parts of these lines. So the way that we say that they are just the same size is not equal, because that would mean that they're the same exact angle. They're equivalent. We say that they are
congruent.
Very good. Congruent. Meaning same size or shape, but not necessarily the exact same angle.
Would corresponding angles also be another way to say it?
Not quite, Adam. We will get there.
Okay.
And let's go ahead and get there. What if I had 2 what are called parallel lines, meaning if we were to extend them out around the world, they would never intersect or touch. But rather than just having 2 lines that do intersect at a point and creating those 4 congruent pairs, 1, 2 there, and 1, 2 there. What if I have these parallel lines, but this other thing called a transversal that intersects both of those? Well, now there's a bunch of different types of names that we're going to talk about. And you can see the one at the very bottom there is the one that we just reviewed. So give me some examples. And we saw when 2 lines intersect, it creates 4 angles. So since there's another set of lines with that, we're going to have 8 angles in total. And you can see a couple of pairs of vertical angles. Can anybody give me some? 1 and what?
1 and 4.
1 and 8.
Careful. 1 and 4
1 and 4.
would be vertical, right? And I'm just going to go in order. 2 and what?
2 and 3.
3. Good. And then the other line in the transversal.
5 and
5 and 8. Good. And
6
8. 6 and 7.
And what do we say is true about all those pairs?
They're congruent.
Congruent. Same size. That's right. Very good. Now, we're going to talk about these alternate interior and exterior angles, and then one that Adam and a few others have run into already on the homework called corresponding. Okay. Alternate, meaning that they alternate the sides of this transversal. I'm talking about the left side versus the right side. Okay. And then interior and exterior, talking about compared to the parallel lines. Interior being these ones inside, exterior being the ones on the outside. So give me a pair of alternate interior angles.
3 and 6.
Very good. Is that the only pair? 3 and 6?
4 and 5.
Excellent. 4 and 5 would be another. Any others?
That's
No,
it.
those are the only ones that are even on the inside. Those are our only options. And notice we picked 3 and 6 because they are on alternate or opposite sides of our transversal. And what does 3 and 6 look like?
The same angle.
Very good. How about 4 and 5? So our rule is that they also are congruent. If you watch the videos, I kind of explain why these are, and I go through the whole spiel. But again, this is just a quick overview and review. Okay. Well, then how about alternate exterior angles? Our only options, 1, 2, 7, and 8. None on the inside of those parallel lines. But if we're looking at 1, they also need to alternate our transversal. So 1 and what?
1 and 8.
Good. And what do those both look like?
The same.
Yeah, the same size. And how about 2 and what?
7.
And what do those look like?
Same size.
Very good. So we got 1 and 8 and 2 and 7, and you guessed it, they are also the same size or congruent. Now, how about corresponding that Adam and a few others brought up? What does it mean to be a correspondent on the news? What if I go ahead? I'm sorry, Darlene, go ahead.
It's the same, but in different places.
Yeah, very good. So we're talking about the same news story, say the big earthquake in Haiti that just shook them and killed hundreds, right? And you, Darlene, actually went there as a correspondent to talk about that while I'm back in the studio. Okay, we're still talking about the same thing. Well, check this out. What if I took this line M here and I just moved it down my transversal? I literally took it and slid it down. What would it eventually become?
5.
It would become line N, wouldn't it? If I was to just slide this down the transversal, wouldn't it become the exact same line?
Yeah.
Because they're what?
They're parallel.
Very good. And that's the only way that they would overlap. And that means if I took these 4 angles that were created by line M and I slid it all down, what is angle 1 going to become?
Angle 5.
5.
That's right. And angle 2 will become
6.
6, and 3 and 7. So I use that analogy about a correspondent with the news. They're talking about the same story, just in a different place. Okay, but that means we're dealing with the same place, right? For each one of these angles we call corresponding. And therefore, what obviously is going to be true about 1 and 5, or 2 and 6, or 4 and 8.
That they would all be corresponding angles.
Meaning,
That they would
Equal.
all be equal.
good, and we're going to use the word congruent rather than equal, because obviously angle 1 and angle 5 are not the exact same. They're in different places, but we do know that they're the exact same size. Okay, so very good. I'm going to minimize this just a little bit so that you can still see the drawing on example 2. And then we're going to talk about these, what are called same side interior angles. So we're going back to the inside of our parallel lines, which means not these, but 3, 4, 5, and 6. But rather than alternating like 3 and 6 or 4 and 5 of my transversal, we're going to talk about the same side. The same side of my transversal line. And what does 6 and 4 look like? Do they look the same? Do they have that relationship of congruency?
No.
No.
Definitely not. 6 is acute and 4 is obtuse. But check this out. Don't we know 6, if we slid it up, would be the same as 2? Aren't these the same? And if I was to look at this, which we call a straight line, what if I measured from there to there or there to there? How many degrees in angle measurements do we know that would be?
Should be
180.
180.
Good, because we know a full circle is 360 degrees. So if we cut it in half, we're looking at 180 on each side. Right? That's that straight angle we talked about last week. So since we know these two are, what do we call, what's the one word we made up for two angles adding to 180?
Supplementary.
Supplementary.
Good. And because we know 2 and 6 are the same corresponding angles, then we know because 2 and 4 are supplementary, then since I can rewrite this as 2, so are these same side interior angles. So I'm going to use a different color to denote a different rule. And we're going to say that angles 3 and 5 and 4 and 6 are supplementary. And I wanted to remind you one more time what supplementary meant. What are supplementary angles? We said their sum is 180 degrees. Okay. Now you can give me tons of pairs of supplementary angles, so I'm not really worried about you filling this in. Obvious ones, 1 and 2, 3 and 4, 5 and 6, 7 and 8. But we also could have gone this way, 2 and 4, 6 and 8, 1 and 3, 5 and 7. So if you want to write any of them down, go for it, but not necessary. Okay, that's stuff that you should have already worked on last week when we first introduced complementary and supplementary for that sum of 90 and sum of 180. Just as a reminder. Okay. So on finally to the entire namesake of this course, trigonometry, the geometry of triangles. Okay. And what a better place, I say, to start with triangle measurements is on the inside. All this, remember 1.1 was titled angles. And so how many angles are there in a triangle?
Three.
Good. Wasn't a trick question, everyone. It is literally stated in the name triangle, 3 angles. Okay. What is the sum of the 3 angles in a triangle?
One eighty.
360.
Ooh, careful. One person said 180, another said 360. It is 180, but do me a favor. Answer me this. Does anybody know why?
360 is a circle.
Okay, good. But we're talking about triangles, Matt. What does the circle have to do with us? Nobody knows why the sum of a triangle is 180?
Would it be because it's angles?
What about its angles?
So the angles, so you said they were complementary and supplementary angles.
Uh-huh.
So that means that the sum of both sides of an angle on a line equals 180.
Hmm.
So,
It's not easy to explain, is it?
I have an idea. I just can't get it into
Would
words.
would it be because of the name? The triangle, so it's 3, and then we add on to.
Yeah, good. I like that. You're trying to put it together.
Uh,
Triangle.
it's
Just means we have 3 of them. We don't know their size though, right? Go ahead,
Yeah,
Harlan.
Because is it because none of the angles can be obtuse, so none of them can break 90 degrees.
So we cannot have a triangle that looks like this, where it's an obtuse angle.
You cannot
Oh,
have
okay.
2 obtuse angles in the triangle, because then the lines won't meet.
Good. That is correct, William. But none of you guys have answered my question.
It's the addition of all 3 interior angles.
Absolutely. But why is it 180 degrees? Well, none of us know, so let me give you 2 quick proofs. If I was to draw a square, by definition, we know that all 4 sides are the same and all 4 angles are right angles, 90 degrees. And so we know 90 times 4 is 360. Who cares? We're not talking about squares. We're not talking about circles. We're talking about triangles. So then what if I took this and I just cut it in half? Do you see a triangle that I just formed? Well, if the whole sum is 360 degrees and I cut it in half, then what does that mean each of these 2 triangles would have to have a sum of?
180.
180.
Half. That's right, which would be 180 degrees here, 180 degrees there. Now that's kind of cool, that kind of makes sense, but it's not really a good proof. That's one that my student came up with yesterday, and I liked the explanation. I sometimes use it, but I want you all to do me a quick favor. And I know we're taking a little bit more time on this, and I let you guys kind of think on your own. Grab a piece of scratch paper. Okay, just any size paper, doesn't matter. Real small or a real big one. Okay, everybody grab a piece of paper. And do me a favor. Draw a triangle on it by using 2 of your sides. Okay, so all I'm going to do here is I'm going to draw from one edge to another. Any size. Everybody see that? Now, obviously, this is what kind of triangle?
A right triangle.
Very good. But it's definitely a triangle. And I know it's a triangle because I have all 3 angles. Can you guys see those? Sorry, I know the background thing is going in and out. And because I have all 3 of those angles, we want to know they're what?
So
So you know what I want you to do? I want you to fold, or if you have scissors handy, create your triangle, okay? Grab that triangle and fold and tear it out. So here's my triangle. I now have it. You can see my angles are still labeled. Okay, and with that, I'm going to rip each and every one of my angles off. Okay, give me a second here to do that. You guys hopefully are doing it as well. Again, remember the namesake is a triangle. So now I've taken and ripped out. You see all my angles are gone? Because what I want to know is what their sum is. And so I made these little arcs to let you guys see the angles. I want you to now take those and combine the angles, because that's what we're trying to do, is add them all up, right? So connect your arcs to be one big arc. And hopefully you guys will see what have you created.
a semicircle.
Very good. And we know half of a circle is exactly what?
180.
180.
180.
Mathemagic. Pretty cool, right? That's a much better proof than just cutting this random square and saying, well, yeah, if I cut it in half, it's probably still just, but we can't see that. We can only see that this is 90. We don't know what this angle or this angle is. But you know that half of a circle is 180 degrees, and that's what all three of your angles with that triangle should have measured up to be. Okay? So not only do you need to memorize what it is, now you know why it's that. I wish I could just get up and walk away right now because that's awesome, right? But I can see some of you enjoy it. The others, I don't even know if you're here. But what we're going to do is make sure that we utilize this fact in many different ways. Okay? And we're going to state a few of these things like we did last week in 1.1 with the angles. But we're now going to be talking about triangles based on the inside and outside. So let's start with the inside. If the size of the largest angle is less than 90 degrees, what did we call an angle that was less than 90?
Acute.
So guess what we call a triangle that has all acute angles?
You try.
Yep. And I'm just going to abbreviate without writing out the word triangle with the symbol. It's called an acute triangle. What if it's equal to 90? What do we call that? What kind of angle?
Right angle.
Right angle.
Right you are. So we will call it a right triangle. And if it's greater than 90?
Obtuse.
And as William said earlier, we can only have one of those. How come? What do we just get done proving? What is the sum of the entire, all three angles in a triangle? 180.
180.
And if we have an obtuse angle, that means it's bigger than 90. We cannot even have two right triangles. Or excuse me, two right angles in our triangle. Because that would be 90 and 90, which is 180. There's not room for a third. Okay, so that's why I said the size of the largest angle. All right, how about the number of, what does that symbol mean again?
Congruent.
Congruent, meaning the same size, right? What if there was 3 congruent sides in our triangle, meaning they're all the same size? What kind of triangle would that be?
Equilateral.
Very good, Adam. How did you know that, Adam?
Because it's all equal.
Because what?
It's equal.
But
Like
how
the
did-
sides are all the same.
How did you know that, though? How did you know that term?
Video.
Look at that.
Elementary.
Some people said because of the video. They actually watched the videos, took notes. That's what you're supposed to do at the beginning of the week. That's why we're not meeting on Tuesday. All right. I wanted to not take away more of your time, but you guys got to use it. Okay. Pretend that we have class Tuesday at 2 and watch the videos, do the homework. All right. How about two sides?
Sausage.
Good for not. Spelled a little weird. Isosceles. And what if there's one side that's the same, which means none, right? What if there's no congruent sides?
Scalene.
Excellent. So we can put insides and outsides together. What if I had a right triangle that had 2 of the same sides? We'd call it a right isosceles or an isosceles right triangle. Typically this and then that, inside out. All right. If I had an acute scalene, I know all of the angles are less than 90 and none of the sides are the same. All right. So if you hear these terminologies, they're already telling you stuff about either the inside or the outside or both. All right. There's what they look like if you wanted to check it out. And here's how we tell you about the outsides with these little tick marks. 1 here, 2 there, 3 there, meaning they're all different sizes. Same there and there, same sizes. Okay. And if the side is the same here and here, then the angle that forms that side, that angle, and the angle that forms this side, since they're the same, so are these two angles. Okay, so those are things that we can utilize, such as this. What do we know all of these three angles have to be?
60.
Equal.
Good. And not just equal, very good. We also know that they have to be 60 degrees, because the only way that all three can be the same and still add up to what?
180.
Would be 60 times 3. Very good. Awesome, guys. So if you could only describe one word with these two shapes, don't say Stussy, all right? What would it be about the two shapes comparatively?
Similar?
Very good. They are what are called similar. They look very similar. But what's true about one versus the other?
One's bigger than the other.
Very good. How much bigger?
3 times.
Sure. Good. We don't know. Now, just by rotating it, you can see that they definitely look similar. But one is definitely bigger than the other. Is it twice as big? Is it 3 times as big? We'd have to know more information. Okay. And of course, I'm generalizing it with these fun little shapes that I used to draw in elementary school on my notebook, right? But we're going to be dealing with triangles. And we kind of already talked about that in the first group quiz last week, right? Similar triangles. And so do you remember, sometimes they'll tell us, right? If I was to take this and make it larger, you can see that they are actually what now?
Same size.
Good. They are congruent, the same size. Not the same. I would have to do this to make them the same. Okay, but this means they are congruent. All right, so we're going to be talking about triangles, of course. So what should we call two triangles that are exactly the same shape but not the same size?
Congruent.
Careful. Read it one more time. Exactly the same shape but not the same size.
Similar?
Very good.
Proportional, right?
Yeah. But what if they are both same shape and size?
Agree.
That's right. So what is the difference? We'll talk about that, but before we do, answer me this. If two triangles are congruent, then do they have to also be similar? And again, think about this before you answer. And then the other way around, if two triangles are similar, then do they also have to be congruent?
No.
Oh,
Good. So let's answer number 1 first. True or false? If they're congruent, do they have to be similar?
true.
Yeah,
True.
because remember, we said that it meant same shape, but not size. And here they are same shape and size for each of these. So if they are congruent, that means they are exactly the same shape and size, where similarity, they don't have to be. So they definitely are similar. Actually, even better, right? So for this, true, and therefore for this, if they're similar, does that mean they are congruent?
No.
Very
No.
good. That one would therefore be false. They look the same, but they're not the same size. So what significance does each have to one another? What's true about congruence?
They have to.
Let me rewrite this.
The angles are the same, and so are the length of the sides.
Good. But similarity, and notice I put corresponding, that's key. What are corresponding sides? The angles will still be the same, right? So if I draw a triangle like this size, and then I draw one a little bit bigger. Notice this angle and this angle will be the same. This angle and this angle, and then that one and that one, corresponding. But don't forget, sometimes they can get a little tricky, and they can take that and rotate it around to try to confuse you, throw you off. Right? You need to know which ones still match up with what. All right. What's going to be true about the sides, though, when we were talking about those shapes up here?
The side opposite of the angle will be the same.
What do you mean by opposite? What's going
So
to be
like
true
right there,
about this side and this side? Those are called corresponding sides, right? What's going to be
Correct.
true about them?
that they're going to have the same ratio.
Very good. Excellent. Good. They're going to have some ratio, or we call it proportionate, when we have one ratio equal to another, right? So if we have, for example, A over B is equal to X over Y, then this is what is called a proportion, right? So if I told you that this was a length of 2 and this was a length of 8, what would you know is true about this triangle compared to this one?
It's 4 times the size.
What is 4 times the size, Will?
That length right there,
And
or that side,
and all the
the
others.
angle. Okay.
Not the angles. The angles will still be the same, right? That's what's true about corresponding angles for both of these. They're always going to be congruent. But if they're congruent, then so are the sides. But if they're similar, then they're proportionate. So if this was 2 to 8, and I told you this was a length of 3, then we would know that this would be a side length of what?
12.
Very good. Because we knew that this was a multiple of 4, well, then this has to be as well. Okay? We say that they are proportionate to one another. Very good. So I don't want to do this example, but I did want to show you how we could figure things out. I can't remember if it was in this class in the discussion board I was talking about, or I was reading through a discussion post that people said they either want to go and check out Mount Rushmore or they've actually been. So I can't remember if it was this class or not because I had 4 classes and so many of those to read through. But if we knew that Lincoln was 6 1/3 feet tall and his head was 3/4 of a foot in size, long ways, and we knew that the carving at Mount Rushmore of his head was 60 feet tall, which, by the way, this is freaking cool, isn't it? Pretty amazing that they did that and how good it looks. We could actually figure out if they wanted to carve the rest of it out, if they had room to make it, what would we say? What one word?
Proportionate.
Ah, very good. Proportionate. Because we could take the actual size of Mr. Lincoln, and then we would take the size of this. And we put this on here just in case you don't know what Lincoln looked like. All right. So how would we set this up? And then we'll just leave it at that. We won't actually finish it. Here's the cool thing about similar, whether it's triangles or figures. All we have to do is pick whatever we want. If we want to do the body compared to the head length, then we got to make sure that we do that same over here if they're going to be equal. Okay, but if you want to do the head length over the body length, then you could do that as well, as long as you do it equally to the other side. You could actually do his head length over the head length of the actual person versus the mountainside. And if you do that, then obviously we're going to do body to body, but we just got to make sure that we're consistent. The body of the person was on top over the mountain on bottom. So the cool thing is you have tons of options as long as you are consistent from one side to the other. It's all good. It will still give you the same result. Okay? The only suggestion that I ever want to make with you all when you set these up is you're going to have that, as I mentioned before, x over y equals a over b. And if we're trying to solve for x, you always want whatever you're trying to solve for on top. Because how do some people know how to solve these? Some people call it cross multiplying or the cross product. Some of your high school teachers probably told you it's called the butterfly method. All right, whatever it might be. I don't like to do all those gimmick things because people don't understand why they're doing it, why it works. What I want to show you is a quicker way to get there. Because if I multiply, I will get x times b equals a times y. That's one step. Then to get the x, I'd have to divide by the b. That's a second step to getting my x by itself. You know what I want to do? I want to do one step. What's being done to the x?
Dividing.
How do we undo? What's the inverse of dividing?
Multiplication.
And as
Okay.
long as I do that multiplication equally to both sides, and I cancel that y over the y, which gives me my 1x, then I know exactly what my answer is. I just got to work it out in one step. Okay, so that's how we would set something like this up. This one would not be very fun because they gave us fractions, and that's what we would be putting in our fractions. So again, I just wanted to kind of talk one, show you how some of you that either went or want to go to Mount Rushmore, you could actually figure out some of these cool things without having to scale up there and climb down and get caught in his nose or something. All right. All right. That's it for that first section. 1.2 for this week. Now let's get to the more important sections. That's 1.3 and 1.4. And I say more important because up to this point, 1.1 and 1.2 have all been very much classifying things. Well, now we're going to talk about what it means to actually get into trig by classifying and defining their functions. Okay? We're going to start with this thing called the Pythagorean Theorem. Anybody remember that?
A squared plus b squared equals c squared.
Good. When is the only time that you can use that?
Right triangle.
Right, you are. Very good. Excellent. And what is obviously the most important letter in that equation? A, B, or C?
C.
Which one was it?
C.
As in yes. Very good. C. That is correct. So when I label this, I got to make sure I put the A and the B. We call those the legs. And C is always going to be our, what we call hypotenuse. And the hypotenuse is always what is called the, that's why we give it a special name, longest side. Why is it the longest side? Well, remember in a right triangle, what do we know that is equal to? What measurement?
90 degrees.
And what do we say the whole triangle had to add up to be?
180.
which means if this is 90, how much is left for the other two angles?
90.
Very good. So they definitely, since there's two of them that have to add up to be 90, and this one is 90, it's definitely the biggest. And since this angle here was formed by these two sides, we know that it forms this third side here. Okay? Do you guys know what POTUS means? Have you heard of POTUS before?
President.
Very good, Jordan, you better know that. POTUS means President of the United States. And there was actually over 367 original proofs of the Pythagorean theorem and why it works. It's obviously a pretty big discovery if it has that many proofs. And one of your former POTUSes, number 20, his name was Andrew Garfield. Not just the cat that liked lasagna, all right? He was actually interested in math and science, and he was a senator and then went on to be the president. He actually has an original proof of it. I attached the YouTube link here, or you can just Google it, all right? If you guys want me to put that into the chat later, let me know. All right, pretty cool. I'm not going to give you those proofs. I'm not going to show you. I'm not going to spend the time on it, but have you heard of a thing called a Pythagorean triple? Because when I give you any two out of these three pieces, you should be able to find the third. And most of the time, when you're squaring things, you're going to have to undo that by taking a square root. And are there a lot of numbers that when we take the square root, we get out a nice whole number? No, you know a few of them. 1, 4, 9, and so on. There's not a lot of them. You can see that the gaps get larger and larger. All right. So we call these things Pythagorean triples. When all three numbers in the Pythagorean theorem come out really, really nice. Whole numbers. Does anybody know any of the Pythagorean triples? Can you give me three numbers that make this true, that work really well?
3, 4, 5.
Ah, very good. That is the Pythagorean triple. That is the best one because it's the easiest, not only to memorize, but also to use. Does anybody know any others?
9, 12, 13.
Ooh, close.
5, 12, 13.
Excellent. Any others?
8, 15, 17.
Excellent. You can see they're getting larger. So I'll give you just one more that you may see every once in a while, but you can see that the numbers start getting larger. There's a lot of them, but the numbers just get bigger and bigger and bigger. And remember, we're talking about squaring these things. We would definitely need a calculator for those. And we don't like to use calculators because they take longer and a lot of people think they're just magic. Okay, I want you guys to know why things work the way they do and use your own mind. So these are things that you guys definitely would want to memorize, especially this one. And then these two, this is just an added bonus if you want it. Okay, because if you have these memorized, guess what you get to skip using? The Pythagorean theorem. Okay, you can bypass actually doing it if you have those memorized and you recognize them. Just be careful. You got to make sure that the biggest one is always the hypotenuse, the seat. All right, they'll try to trick you sometimes and give you a 3 here and a 4 there. And people are going to say that the smallest side is 5. Got to be careful. So another one that we will see and use is called the distance formula, but not nearly as much. It's not as widely seen and used. Anybody remember that one?
Is it
Go ahead.
D equals square root x2 minus x1 squared plus y2 minus y1 squared?
Impressive, Juliana. Well done. Anybody know why that is? You're like, because math teachers hate us and they want to just make it as hard as possible. No, well, let me show you real quick. I won't go into too much detail about this. What if I have 2 points and we're either on the X or the Y axis? If I just gave you 2 points, right? say one right here, and then another right here. And let's say that this is 0, and then this is 4. What's the difference between those? What's the distance?
6.
How'd you get that so quick, Harley?
I took the absolute value of 2 from 0, absolute value of 4 from 0, and I added it together to get 6.
So we knew that this was 2 from there, and then this was the distance of 4. So he knew that we were 4 here and 2 there. He virtually counted. All right. What if I did something similar on the y-axis? And I said here and there. And I put 0 here. Let me do the proper. Put 0 here. 1, 2. Now what is it?
7?
Did you do the same thing?
Yeah, basically.
From 0, he counted 2 there and then 5 there. Now what we can always do, if it's on a horizontal or vertical line, is we can take the bigger number and subtract the smaller number. We're just trying to find the difference between those numbers. And I know a negative times negative becomes positive. There's our 6. Same thing here. My bigger number and smaller number. So I would take 2 and subtract the -5, which gives me that 7. But what's going to happen if I'm on a point right here and here? How are you going to find that distance now?
Need a ordered pair, right?
Good. And so let me show you why. All right. What if we wanted to get a point on our grid? Well, we could provide what is called an angle of rotation and a distance. So if I wanted to get from, say, this point to this point, we could do that. We could find this distance here. All right. But I could have also just told you, if I'm starting at the origin here to get to this point, I could just tell you, go out this far and then rotate this angle with this distance, and you could get to that same point. That's what we'll do eventually. But like Jordan said, most likely just give me the x comma y. I'll march over x and I'll march up y, and that will get me to that point. But the quickest way is not going over and then up. It's just going directly there, isn't it? So we want to learn more than just one way. But if I give you these, can you find the distance between them now? Rather than just having an x and a y? Well, what are those values? And what are these values? Well, this is some x and this is some other x. So I'm going to call this my first x and that my second, some y, some other y. This is my first and that's my second. And I know if I actually marched from there to there, and then from there to there, do you guys see what I just created?
Right triangle.
A right triangle.
And what did we say we could always use in a right triangle if we knew 2 out of the 3 sides?
Pythagorean Theorem.
So if I can figure out what this distance is and what this distance is, then I would be able to find out this distance that I want to know. But as Harley was helping us on the previous one, do we know how to find horizontal and do we know how to find vertical distance? Yeah. We just take the bigger one and subtract the smaller one. So then what's definitely the bigger one on my x's? Well, further to the right, the bigger it is. So I will literally just take x2 and subtract the smaller one, x1. That's the difference or distance between those 2 points. How about with my y's? Bigger minus smaller. And now do I quote unquote know what this length and this length are? Then I should be able to find that one. It's easy. I will take my a squared plus my b squared and set it equal to my c, or distance between those 2 points squared. But of course, we want to know what the distance is, not what the distance squared is. So what am I going to do? To keep it equal, I got to take the square root of both sides to get that d by itself. So now you guys can see why some of these nasty things are the way that they are, and not just memorize them as one out of all of you did. Okay, hopefully this will help you to understand why some of these things are as nasty as they are. It's just the way it works, given what we know or don't know. Okay, so again, don't worry too much about memorizing that. I care a whole lot more that you memorize the Pythagorean theorem and the triples for this class. All right. So finally, our main point of today is to get to that point. And so what we're going to do is talk about how to get there. And we said the quickest way to get there from the origin would be by going straight there. But in order to do that, I would have to take some distance and I'd walk it out to the x, and then I would rotate it over a certain angle to get there. And you guys can see that, right? See that angle that I'm forming from there to there? Now, if I kept doing that, I went out some distance and I went from there to there and I kept going, what am I going to end up forming?
Circle.
But we already know how to get there, don't we? It told me go sum x comma y. So I would go right x and up y. And of course, what is this class called? Trigonometry, the geometry of triangles. That is going to be the basis of this entire class, is you being able to, with whatever they gave me, draw a triangle. And what do we hope we get? What kind of triangle?
A right triangle.
Because we can use the Pythagorean theorem to find this distance, or like I mentioned, we would form a circle. We're actually going to call it r as the radius of that circle going out. And we're going to have this angle in here. We're going to use a Greek letter called theta. All right. And what we are going to do is we are going to use this to come up with all of the trig functions. And are you guys familiar with the trig functions?
Like cosine, tan.
Yep. Those are the big three. There's also cosecant, secant, and cotangent. And those are a lot to say and write. Saying it's a little bit quicker than writing. So to help with our writing, we're going to just take the first three letters of each and every one of these, other than cosecant, because that is already taken here for cosine. So the only one that's going to be a little bit different looking is cosecant. We're going to have to rewrite as CSC for cosecant. Right? And the relationship between each of these pairs is that they are reciprocals of one another. And hopefully you guys all remember what reciprocal means. Does everybody remember the acronym from geometry, probably in high school, that you learned in order to memorize these trig functions?
SOHCAHTOA.
Very good. SOHCAHTOA. And remember, that's just for the big three. Because if you know these, then to find the other ones, we will just take the reciprocal. And the reciprocal means if you know 1 is 1/2, then the reciprocal of that is flipped, 2/1. If you need to make a note of that, reciprocal is if you have A over B, it becomes B over A. So if I asked you to find sine, cosine, or tangent of anything, we're going to talk about angles, right? You guys got to make sure that if I ask you for the sine of something, that right there, what you just wrote, is a sin. Do you guys see it? It says it. That's a sin. What do I mean by that? With all of these trig functions, you need a what accompanying it?
Theta. Angle.
You need an angle. That's right. That's the only way that you can give me all of these ratios out. So instead of just taking the opposite of that angle and the hypotenuse, which would be y over r, if we're on an xy axis. Okay, if we don't have the x and the y axis, then yes, you will still use what you used in geometry. But now I need you guys to memorize these. Okay, how about cosine of theta and tangent of theta?
X over R.
Good. Cosine is going to be the adjacent, not the opposite, but adjacent over the hypotenuse. So x over r, as somebody mentioned. And then tangent.
Y over X.
Opposite over adjacent, that would be the y over x. And if you guys have those three memorized, then it's going to be real easy to find cosecant, secant, and cotangent of that angle, whatever it might be. What are they going to only change as? One word.
Reciprocal.
Reciprocals.
Very good, very good. The reciprocal, which means what would cosecant be?
R over Y.
And r over x and x over y. Excellent. So let me show you how they will give us some of these. What if I asked you, and I'll leave that down there just in case you need to still write it down. What if they asked for all 6 trig functions, yet they only give me a point, an ordered pair? -4, -3. What's going to help you a lot in this class is drawing these things out. So what am I going to start by drawing?
A graph.
Yeah, my grid. And I know I'm only going to be in this quadrant where it's left 4 and then down 3. But notice, guys, what are the only things we really need up here in order to come up with all of these?
Triangle.
X, Y, and what?
R.
R.
Thank you to all my pirates out there. The R, that's right. So if I can come up with that triangle, as somebody said, and I find all 3 of those points, beautiful. So then what is -4, -3 telling me? From the origin, go left 1, 2, 3, 4, and then down 3. And that will take you to this point, which I know to get there, I would just go straight there, and that would be a whole lot faster, right? But we also know that if I go left 4 and down 3, what have I just created? Not any old triangle, but a
Right triangle.
and
Right.
that right triangle allows me to use what?
Pythagorean theorem.
So,
As long as I know 2 out of the 3 parts, we can find it. And does that mean that we have to use the Pythagorean theorem?
no.
If it's a what, we can skip it.
Pythagorean triple.
And is that a Pythagorean triple that I told you would be in your best interest to memorize?
Yes.
Yes, it is. It is a 3, 4, 5. And remember, our radius is always a distance from the center out in some direction of my circle. And since it's a distance, it will always be what?
Positive.
Very good. You didn't sound like it, but very good. It is positive. Okay. So very good. Our radius will always be positive, but the X and the Y, depending on what quadrant we're in, will be either positive or negative. Okay. So if you can tell me very quickly what the sine of that angle theta is, what the cosine of that angle theta is, and what the tangent, even though they asked for all 6, we're pretty much going to be done, aren't we?
Yeah.
Because we know that cosecant is just the secant, and cotangent are just the what of all of those?
Reciprocals.
Very good. Excellent, guys. So what is the sine always? The what over the what?
Y over R.
So I got my Y and I got my R. And if you guys want to, you can even label. Here's my Y, here's my X, and here's my R. So I should be able to very, very quickly go through this. And in reality, I'm just going to do these 3 and then flip, flip, and flip. Just make sure nobody really gets these 2 mixed up. But a lot of people will get these 2 mixed up with these 2. A lot of people see the S's and they'll put those together, and the C's and they'll put those together. So the way that I taught myself how to do this in geometry in high school was I read it from right to left. Now that doesn't really help me with this one because it looks the exact same. But this one, it looks just like COS. So that's how I help myself to remember which one went with what. Okay, Jacob, you got a question, buddy? Go ahead.
I'm sorry, I missed it. How do we get 5 for R?
So instead of actually physically doing our Pythagorean theorem, a squared plus b squared equals c squared. Great question, by the way. And putting in our X and Y in no particular order, our 2 legs. We knew the hypotenuse was this one, and that's the R that we were trying to find. I told you guys you can skip that. 9 plus 16 equals R squared, which is 25, which then I'd have to take the square root of. And remember, if you take the square root, you have to take the positive and the negative case. Because when I square 5, I get 25, and when I square negative 5, I get 25. But remember, we said that the R will always be positive. So how did we skip all of this? We knew that this was, go all the way back up to the top. I think I went a little too far. Where is it? There it is. Our Pythagorean triples. And one that I told you for sure you need to memorize.
So in case we have one that is 5, 12, then we know that's going to be 13.
I'm fine with you skipping doing the Pythagorean theorem and just putting that in. Just tell me how you knew. Triple. It's a triple. And I'll know you knew it. You didn't have to do it.
Okay.
Absolutely. Now I will give you guys one more hint. They will try to fool you sometimes. Do you guys remember the similar triangle stuff we talked about? And how all the sides are what to one another?
Congruent.
Close. If they're similar triangles, the sides were proportionate to one another. Very good. Which means instead of them giving us 3, 4, and 5, whether they're positive or negative, that just depends on what quadrant we're in. They could double all of those. And they could have put a 6 here and an 8 there. And if you see that those are all just the 3, 4, 5 multiplied by what?
2.
Then you know that that 5 is actually going to be
10.
Does everybody see my 3 times 2, my 4 times 2, and therefore my 5 times 2?
Yeah.
So don't let them fool you. I could have put 40 and 30 there. Then you would have known that this was 30, this is 40, so this has to be what?
50.
Yeah. So it can be any ratio of any of those Pythagorean triples we talked about earlier. Yeah, well done, guys. All right, so quickly, what sign?
-2/5.
It's always our y over r. Careful, don't lose your negative. And if I know that that's -3/5, then I also know cosecant of that angle is what?
-5/3.
Excellent. A third of the way done. What's the next one? What's cosine always? The what over the what?
X over R.
X
The
over r.
X over the R.
And we know the x, we know the r. Just be careful with your signs. We get -4/5, which means we know this is -5/4. And then lastly, tangent.
3/4.
Good. Now careful. -3 over -4, which, as you mentioned, is going to end up canceling out to be positive. So then this would be positive, just flipped. Done. As long as you can get those 3, these 3, follow by flipping them or doing the reciprocal.
Professor,
Yes, ma'am.
let's say we have +3 and +4. Would it be the same thing? 5?
Yes, it would.
Okay. Just the
Check it out.
same. Okay.
Make that positive, make that positive. I still, when I square them, I'm going to get +9 and +16, which would give me that.
Okay.
Yep, very good
And then,
question.
so would it change the
only
scene
thing-
and all of them?
Yeah, the only thing that would
Okay.
change is these values,
Okay, makes sense.
whether they're positive or negative.
Thank you.
Yeah, that's a great question. That's a great segue into the very last section for today. I'll wrap it up here. 1.4, using all of those things that we just defined. Okay, now we talked about what they were in terms of x and y just a minute ago. But what if I wanted to write them in terms of only functions? Well, what do I know sine is comparable with? What other function?
Cosecant.
Very good. But they were what of each other?
Reciprocals.
So if I'm going to say sine is equal to cosecant, could I just put this? Are they identical?
No.
No.
They're reciprocals of each other, which means I'd have to flip this. Now, let me prove this one and only one to you, and then we'll fill out the rest of this chart. Okay. What do we know that sine is equivalent to in terms of our x, y, and r? What do we say? What is it always equivalent to?
Y/R.
Very good. So I'm trying to tell you that this is equal to this, which we know is 1 over whatever cosecant is. And what do we say cosecant was equivalent to? What over what?
Sine.
R over y, the reciprocal. So what I'm trying to prove to you is that these are in fact equivalent. And we know that this is equal to that, and we know that this is equal to that, which it happens to have the 1 over, right? And do you guys remember one of those things I told you that was, I don't know, kind of important in all of mathematics? What is one of the most important things? Go ahead.
Times only by 1.
But not very good. I'm going to multiply this side by 1 because it is way uglier than this side. I'm trying to prove that these are indeed equal. So I don't like the r over y as a fraction in my big fraction. So I'm going to multiply by what is called its reciprocal. So I'm going to multiply top and bottom by y over r. Does everybody see my fancy 1 here? Anything divided by itself is just 1. But the reason I did this was so that I could multiply the denominator, because I know that cancels out to be y over y, which is 1, and r over r, which is 1. And now notice oh, that's just a big 1 and I can forget about it. Which means all I have left on top is my y over r, which is exactly what we said this was. So does everybody agree with me that this is a true statement? Good, because I don't want to do all the other ones and prove it to you as well. I just want you to fill it in. What is cosine going to be equivalent to?
1 over secant.
Very good. The easiest one, tangent. What is it equal to?
1 over cotangent.
And if we know those, then what should the others be?
Just
That's right. So this is an alternative way to write these. And do you think that we're going to be going left to right on many of these occasions? Probably not. If we have the things on the right, then we'll probably rewrite them in a simpler form like we have on the left side. Okay? But it's good to know that we can do that because they are equivalent or identical. Okay? So there it is. And therefore we call these reciprocal identities. Why'd they name them that? What are they? Identical. In what way?
one.
They're reciprocals. They're flipped. Very good. All right. So somebody mentioned about our signs. And remember when we had our number line and then we did another one, we called it the X and the Y axis. We then split it into 4 quadrants. And remember we said we'd start in the positive direction. So we know that if we were to graph this, it would be a positive comma positive. And that's why we started there. And then we said, all right, well then if we're going to go this direction for our angle, we might as well continue and go to angle 2, which we then know is going to be negative, positive. And then here, negative, negative. And then here back to positive for our direction in X, but then negative for the Y. So if we looked at all 6 trig functions, the sine, cosine, and tangent, didn't we just say how they are related in X, Y, and R's? What did we say? Sine was always. And therefore cosecant. Cosine always. And therefore secant. And tangent always, and therefore cotangent. What we want to do is make sure that we don't have any issues like somebody asked earlier. I can't remember who it was now. About the positive or negative stuff. But if I know that the R's are always going to be positive, then I don't have to worry about those. And I can just focus on only the Y value for sine and cosecant, or the X value for cosine and secant. And since I know that the sine is always the Y values, I know that for this splits the positives for the Y values and the negatives for the Y values. So then I know what's going to be positive in quadrant 1, what's going to be positive in 2, 3, and 4. And I'm going to give you guys a little acronym to be able to know what is positive where. It is all students text in class, or all students take calculus. Okay, whatever, you can make up your own if you want. Okay, that then tells me what is positive where. All students take calculus. What do you think the A stands for?
All.
Every single 6 of our trig functions is going to be positive in this quadrant. How come? X and Y are both positive, and we know R is always positive. What is the only trig function that will be positive in quadrant 2?
Sine.
Now, don't forget, sine and cosecant, they're going to be the same as far as their positive or negative signs go. Okay, so when we say we're only talking about these 3, but their reciprocal partner follows suit, because they'll just be flipped. That's not going to change whether they're positive or negative. Okay, good. So everything above the x-axis for sine. For cosine, it's going to be everything to the right, because that's where x is positive everywhere. And that's the only thing that affects cosine. So that's why quadrant 4 and 1 are the only things that are positive as far as that goes for cosine. The weird one is tangent. It's positive, as all of them are in quadrant 1, but also in quadrant 3. How come? Well, remember, if it's going to be positive, that means x and y have to be the same sign. And definitely here, but also here, just like we ran into on this one. Negative, negative. All students take. Notice the only things that are positive are these. The rest of them are negative. So like somebody, I think it was Martha, had asked, how do we know if it's going to be positive? What if they're switched around? Is it still going to be 5? Yes, the length will still be 5, but the signs of these things would change depending on which quadrant we're in. So this is a way for us to make sure that we know when things are positive and when they are negative. You guys cool with that?
Yep.
All right. Well, then let's wrap this up with the last 2 things for this week. And these are what are called identities or identical formats. And remember, to get to that point, we can always go directly there, but we'd have to know that distance and at what angle to rotate. Most of the time, they're going to give us an X and a Y. And how would we get there if we did that? Right some X, up some Y, and that is our right angle. And therefore, we will then call this angle that we're going to rotate theta, and that if we kept rotating around that distance, we'd have a radius length. So we'll call this R. And what do you guys know that we can use if we know 2 out of the 3 of those?
Pythagorean theorem.
Very good. Excellent. The Pythagorean theorem, Darlene said. But I want to actually take this and write this in terms of sine, cosines, or tangents. And since this is an equation, I can do whatever I want to it. And if I want to divide all of these by r squared, I can. So I'm going to. Because now I can write this as x over r with the whole thing squared, so I don't have to write it twice. Plus this one, y over r with the whole thing squared. And we know anything divided by itself is 1. Now, why did I write it like this? Well, remember, what did we just get done memorizing? What is x over r and what is y over r equivalent to?
Cosine and sine.
Very good. So I'm going to rewrite this as cosine. What do I have to write after every trig function?
Okay.
Theta, some angle, right? Plus sine of some angle is equal to 1. But what am I missing?
Square.
Very good. Where should I put that square?
Before the theta.
Good. I don't want to put it after, because then it looks like I'm squaring the angle. When in reality, we change this out with this. And that whole thing is what's being squared. So rather than having to put a whole parenthesis squared, I'm going to get rid of those parentheses and just let you know I'm squaring the sine theta, or I'm squaring the cosine theta. So that's why they put it after the cosine and not the angle. Just like there was the Pythagorean triple of 3, 4, 5, this is the Pythagorean identity. But remember, there was a total of 6 trig functions. That's only 2 of them. So again, because it's an equation, I can do whatever I want to it as long as I do it equally. And if I want to get some other things involved, before I get there, I'm going to introduce you to these things called quotient identities. Right? I'll come back to that in just a second and give you the other 2 forms of it. Quotient identities are when we take something like sine of an angle and put it over cosine of an angle. And what do we know sine theta is always equal to? Y over R. And cosine is always equal to X over R. But as you guys know, we don't like taking fractions and dividing. So instead, we're going to do our fancy one yet again, and we're going to multiply top and bottom by the reciprocal of the denominator. Because what happens when I do that? Since I'm multiplying, the r's cancel and the x's cancel to be 1s. So now I can forget about this whole denominator because it's all dividing by 1 now. I can concentrate on the top and what happens to the top. The r's also
Y.
cancel. And we're left with what?
Y and X.
And what is y over x equivalent to?
Tangent.
So we just found out that this is equal to this, which is equal to this, which is equal to that. So we are going to say that anytime we have sine theta over cosine theta, we can rewrite that as tangent theta. And because we know a relationship with tangent theta and cotangent theta, what would cotangent be equivalent to?
Cosine over sine.
Very good. Since these are reciprocals, then this has to be the reciprocal. So it would be cotangent over tangent. Oops, I missed. Very good. So to wrap this all up, guys, what I'm going to do over
sorry,
Yeah.
on the bottom you wrote tangent theta. Would it not be sine theta for cotangent?
What did I just write? It was supposed to be cosine over sine. Thank you. Cosine theta over sine theta. Got ahead of myself. Thank you, Will. It's just this flipped. Appreciate that. So the last thing that we're going to do is we're going to go back up here to what we called the Pythagorean identity, and we're going to divide this whole thing, this whole equation, by either sine or cosine. You guys take your pick. Which one do you want to do first?
Cosine.
Perfect. I'm going to divide. Now remember, if I want to keep it equal, I got to do it equally to everything. So what is cosine squared theta over cosine squared theta?
1.
1.
Careful. What did we just get done saying sine theta over cosine theta was?
Tangent.
Tangent.
Since they're both squared, we will write tangent squared. And what is 1 over cosine? What did we just get done saying that was a little bit earlier?
Secant.
Excellent. 1 over cosine is equal to secant. So I can actually say that this is equal to secant squared theta. And there's what is called a variation of the Pythagorean identity. Notice I now have 1, 2, 3, 4. There are also 2 other trig functions to make the total of 6. So of course, we could also divide everything by, instead of cosine squared, sine squared theta. And that would give me my 1. That would give me my cosecant squared. And that would give me my cotangent squared. So again, there are my big 3, or all 6 Pythagorean identities with all 6 of my trig functions involved. What's the one I definitely want you to memorize? Sine squared plus cosine squared equals 1, as long as the angle is the same. So again, 3 chapters worth is a lot to go over. I'd rather not lecture this long, but I wanted to make sure that we're starting off very slow and methodical and making sure that you guys understand all of this stuff, because we're only in week 2. We're laying the foundations for this entire class. All right, that's it for this section. Good luck.